All right, so let's get started. We are on lecture 8. Today we're going to study a certain limit of the dynamics of trainable variables, and it is kind of in between the two limits that we already discussed. The one limit we discussed in the previous lecture, when the learning just starts and the Gaussian approximation is good, you can look to see how the system would evolve and kind of extract from that what kind of properties on the weight matrix you should have such that the learning is more efficient. And we saw that this is related to the Laplacian of the free energy. The other limit we discussed like 3 lectures ago is what happens in the actual equilibrium. So like when or close to the learning equilibrium, when you go there, then you describe non-trainable variable through the statistical ensembles, and then trainable variables can be described through equations like Fokker-Planck or Mandelung or Schrödinger. There's still limit in between that you've already gotten close to the local equilibrium. You are not trying to study the behavior of the microscopic things and the level of probability distribution, and you want to see what would be the probability distribution of the trainable variable. So this is kind of the limit that now we are interested in. Now, it turns out it's related to the phenomena that is observed everywhere in physics and also in biology, that is called self-organized criticality or scale invariance. Now, scale invariance is the phenomena that we observe, and a theoretical explanation that people thought is valid is the self-organized criticality. So let me go through let me explain to you first what those phenomena are, and then we'll dig into the learning theory and see how similar things can emerge from learning. Okay, so experimental facts that we see fractals everywhere. So some self-similar structures that appear at different scales. Now, from the point of view of the phenomenological analysis, all it means that you can identify a probability distribution of some features, and then the probability distributions would be given by this equation, meaning that it's not an arbitrary probability distribution, but if you rescale x by lambda x, that only thing that jumps in front is lambda to the minus some power delta, and this delta is called a scaling dimension. Now, not for many functions, not for all functions, sorry, this would be true. But if p if p of x is a power law, then this equation would be true. And we're interested to see when such probability distributions appear from the learning dynamics. That's kind of the topic of today's lecture. What is interesting to see here is that generically, in physical systems, you would not see probability distributions of that type appearing. And in order to see them, you really have to go through fine-tuning of parameters. So that's something that's called the critical phenomena, is when you tune some parameters like temperature or pressure, then the system, and by tuning the parameter, you find the value where the system is at the point of phase transition. So between gas and liquid, or liquid and solid, and at that time, and at that point of the phase at the phase transition, such scaling behavior or power law correlations appear. Now, we don't know what that means in the theory of learning, but if everything is learning, then maybe there is a way for us to actually see such phenomena in the learning dynamics. Now, the point here was that you really have to fine-tune parameters. That's what you usually have to do in physics. However, what we seem to be seeing in nature is that this happened even without fine-tuning parameters. So there is no fine-tuning of parameters on those pictures. This is filaments of the dark matter simulation. This is lightning, broccoli, shell. So all those pictures illustrate some structures that seem to be self-similar, right? So there are no preferred scale for them, and then similar features are appearing on a wide range of scales. So the idea behind the self-organized criticality was that maybe there is some phenomena that we can identify that makes the appearance of this critical phenomena of or power law correlations without fine-tuning the parameters. So somehow system itself tunes certain parameters. And we'll see that that does happen in the learning systems. Now, why that happens and how we can observe this self-organized criticality or the scale invariance is another question. And then here first I'll present you a theory of why we expect this might happen, and then I'll show you the result of numerical experiments that confirm that that does happen. And that phenomena is actually very generic in the learning system. It's not something that you have to like work hard and find a certain data set, arrange a certain architecture that just happens automatically. And then, analytics will show first why we think this happens automatically, generically, and then numerics to confirm that result. Okay, so let's move on. So let's, and the first step will be not to study a very complicated system, but to study a very simple system, a toy model. And that is usually a good approach in physics when you are dealing with a complex system. Well, don't study the most complex system first. Try to understand how this works at the level of the simplest possible system. So nothing can be simpler in terms of a learning system other than just having only one trainable variables and one non-trainable variable. Now, it doesn't mean that this is actually, we expect this will actually happen if there is, let's say, one neuron and then one weight and nothing else. It is just saying that maybe by looking at only a single trainable variable and single non-trainable variable, and forget about everything else, integrating it out, we can already see what is the reason, what is the analytical reason behind criticality to be formed, behind the phenomena of self-organized criticality. Okay, so that's the assumption. Toy model, nothing really realistic in it. And once we understand how things work for the toy model, it will be easier to extrapolate it to a more general model and then confirm it analytically. Okay, so now what is the assumption we're going to make? The trainable and non-trainable variables have to interact somehow. And what we want to say is that let's assume they interact in the following way. The only function through which they interact with one another is the loss function. And so what we are saying, well, okay, so let's assume the system evolved towards its equilibrium. There are some average value for the non-trainable variable. There's some average value for the trainable variable. So this is just some constant. And now let's expand around that minimum, around that equilibrium state or average state, X and Q. So if you do this expansion, then it will be a Powell-Taylor series expansion here. And so you will see higher and higher power terms appearing, but we'll keep everything only to the second power. Now, the odd powers will not appear because this will not correspond to the minima or maxima or saddle points. And so we ignore the first and third, all odd powers are ignored. Now, the first non-trivial power, and we assume that this, the deviations from the average values is small. So really, the higher and higher orders terms are more and more suppressed. So they affect the loss less and less. So then the first term, you get this. This is just quadratic term. And then you also get quadratic term for Q. And that would be all, but we want to keep all quadratic terms for separately X and Q. And so we will include one more term, and that is the only interaction term between X and Q through which they will actually not form independent probability distributions, through which they will communicate one another. And basically, Q will try to learn X, roughly speaking. So that's our model. This is our toy model of we have no odd powers, only even powers, and only one interacting term. So this is a quartic interaction. So there are 2 powers of Q and 2 powers of X. All those constants, lambda X, G, lambda Q, are some phenomenological constant. It's not important what they are, but we assume that they have a fixed value. Whether they're, again, positive or negative depends on whether our will depend on whether the temperature or minimization or maximization happens on the free energy, and we'll discuss that shortly. Okay, so we have that. Now we follow our usual procedure of applying the maximum entropy principle. And here we first fix Q's, so Q's don't change. And we say, all right, so what we want for a fixed Q, we want the probability distribution, conditional probability distribution to be such that average loss is given by U of Q. So this is written here. And if we follow the discussions that we did earlier, we'll end up with this probability distribution. So this is a canonical probability distribution where we just exponentiated the loss function. Now this constant doesn't matter because it's just proportionality constant. And once we have that, we can find the corresponding free energy, which is again takes a familiar form. Now the only, and we can do this calculations for the reason that this probability distribution is quadratic in X. So yeah, it has this quartic interaction, but as a function of X in the exponent, it's quadratic. So it's a Gaussian probability distribution. And so we can actually integrate it. And once we integrate it, we get two terms. One is this logarithmic term that actually comes from the integration. And then this term over Q, which is just stays here because of its presence in the loss function. Okay, so that's our result. And this is now if we start including higher and higher order terms, like say x to the fourth power, then we will not be able to do this integral, and then we would have to apply some kind of perturbative methods to see the effect of those terms. So we're not going to do that. We're going to keep everything at the simplest possible order. Okay, now before I move on, let me see if there are any questions about the actual model. All right, so let's take, now remember our goal was not to find the probability distribution over non-trainable variables, but over trainable variables. So we have to move further and try to find what this P of Q is. What is the probability distribution of the trainable variables? We'll call it marginal distribution. And then there is overall joint distribution, which is nothing else but conditional distribution that we identified on the previous slide, times this marginal distribution P of Q. So our job is to actually figure out what this P of Q is, derive analytic expression for this P of Q, and once we have it, then we'll go to our numerics and try to see, well, do we get similar distributions or do we not? When do we get those distributions? Okay, so now, again, we are trying to go to the limit where trainable variables are formalized. We're not studying the dynamics of P of Q of 2, or P of Q and of T. So that's something, some more fine grained description. We're just interested to see what is the P of Q, average P of Q. Then in the thermodynamic description, what it means that we try to set a constraint, one more constraint on the free energy of the non-trainable variables, the free energy of x's. And if we set this constraint, then the equilibrium distribution are derived in similar manner, and that will be given by e to the minus alpha f. So now, before we had here e to the minus beta h here, but now we put a constraint on the f, and so will be e to the minus alpha f. The same idea, alpha again plays the role of the Lagrange multiplier, or 1 over alpha plays the role of the temperature now of the trainable variables. Okay, so but we do know what f is. Sorry, so we do know what f is. This, so we can really plug it in and get an expression for P of Q. So this f had the 3 terms, one logarithmic, one quadratic, and a constant. Constant doesn't matter because we are only interested up to proportionality constant. So we're not interested in the constant. Logarithm becomes this power law term, and the quadratic term becomes the exponential term. Okay, so now we see why the behavior of the distribution of Q's will have there will be two different behaviors for the distributions of Q's, or Q minus Q bar. Now, the first comes from this first coefficient, right? So when this term dominates in this regime, so what does it mean that this term dominates? It means that Q is very small, and so this exponent is roughly 1. So this the quadratic term is roughly 0. Exponent is something like 1, and so really only this power law expression dominates. Now, when does it happen? There is a limit in which this happens. There's some special functions defined for that. But anyways, for small enough Q's, you have that behavior. Now, for very small Q's, which are actually negative, and they're close to smaller than negative lambda x divided by g, so very negative numbers, then you get some other behavior. Now, why would I put here a negative number? Well, it depends on lambda x, because if lambda x is negative, then of course this makes sense. But if lambda x is positive, this doesn't make sense because this guy is always positive. Nevertheless, anyways, there is a limit. There is a range of scales when there would be a power law dependence. So exponent would not matter. It would always be 1, and this will be the dominant, will give you the dominant contribution. Now, if you keep going to larger scales for Q, eventually the exponent will start dominating, and that tells you that for large deviations for Q, you will have this Gaussian suppression. Now, remember, the Gaussian suppression is what you usually see in physical theories. The fluctuations are all Gaussian, and that comes from the fact that the potentials around minima are quadratic, right? So if you have a potential is quadratic and that distribution is e to the minus alpha that potential, then it's a Gaussian. And so this is the usual regime. This is the usual thing that you see. However, now because of this learning dynamics, we get this additional term, this factor that gives us a power law-like dependence for small deviations from the mean. Okay. Now the power here is minus alpha divided by beta. So alpha determines what the power is, and beta also determines what the power is. And so we do not expect the dependencies to be different if we had many Qs, and that's something we're going to study. Here is only one Q, and we expect this is the dependence. But if we had many Qs, as we will see, the same power would appear. So you will have criticality, and this is where criticality is. This is where scalar invariance is. So for small deviations from the mean, we see that those fluctuations, those deviations, have to form a power. Okay, now before we go to a general case and discuss what happens when we don't just have one trainable, one non-trainable, but many trainable and many non-trainables, let me note that once again emphasize that this alpha does play the role of the temperature. 1 over alpha plays the role of the temperature of the trainable variables, and that therefore you may ask a question: whether is it positive or is it negative? Now, last time we discussed the situation where at early times it seemed like the trainable temperature of the trainable variables was negative, and that's why it was cooling down the non-trainable variables. And we wanted it, and that's what was our conclusion. Now, at late times, it may happen that the trainable variables will be actually positive. The temperature of the trainable variables will be positive, meaning the alpha would be greater than 1, and then f would be minimized. So those are kind of the two limits. Now, although I wrote this, it's not really clear that you can study at early times the probability distributions of P of Q, because at early times in the training dynamics, it changes rapidly. And so really no equilibrium is established here. But at late times, this is something that you can do. You can run your code long enough and then try to see what the distribution is. It doesn't mean you cannot do it at early times. You can also do it at early times, but it is not going to be a very good equilibrium. It will be metastable equilibrium. But you can do this analysis, of course, at both times. Okay, now, so I'm done with a simple toy model. Only one trainable, one non-trainable. All we're going to do for the rest of the lecture is we're going to first generalize this model for more trainable, more non-trainable, and then see numerical result of the numerical simulations. Questions? Okay, so general model, more general model. Now, remember that first I put this quartic coupling and told you that this is the simplest, the lowest order coupling that you might get. Actually, if you think about the loss function, and especially the bulk loss function, when we had like x minus f of x, if you remember, where f minus f of fwx plus b, so this expression, if you actually linearize it and each term, then you will see terms like that where q's would actually be w's, and there'll be a coupling between 2 powers of weights and 2 powers of non-trainable variables. Now, let's see how that looks more precisely. This is the analysis that we're going to do. Now we have many non-trainable variables and many trainable variables. As before, we impose the constraint, but now this is our h. So this is what I was talking about. Really, in the linearized limit, we have this matrix G, which had 2 powers of w in it, and we have 2 powers of x to it. And so this is exactly the same what we had before. And that's what actually was my motivation for this in that toy model to consider quartic coupling. 2 powers of x, 2 powers of q's. So q's, remember, play the role of the trainable variables like w's. Okay, we also have this v of x, which may be part of the loss or maybe part of the training data set. So you can have a training data set where x is constrained to have something, some minima. And then in addition to this, you will have that. Or you can have this v of x as a local objective term. So if you remember, we've discussed that in your loss, you can have, you can put a local objective terms so that individual neurons are trying to classify, and then there will be negative mass terms or something else. So you can also have this term. Now we are here only considering it as a matrix. Of course, that means we are kind of linearizing around minima. We do it for x and we do it for q. However, despite of that, not only quadratic powers of x and q, but also quadratic powers of x and quadratic powers of q will appear, and that's essential, right? That's what I call the quartic interactions. So you basically follow the same analysis we did before. Now the only difference is the free energy with the trainable variables fixed. So now trainable variables are fixed. We're only interested in the conditional distribution of non-trainable, given that the trainable are fixed. And then you will do the integration, find the partition function, take a log of the partition function, and get the free energy, which is given by this. So this log again comes from the fact that you do take a logarithm of the partition function, which will be just given by determinant of cell power of this quadratic form. Okay, so this will be your expression. We don't care about any additional constant that you would put here, because constants would not change our probability distributions. They will just be absorbed into normalization constant of the probability distribution. Okay, so that's our result. Again, logarithmic term, and again, quadratic term, just like before. The only difference here is now we really have a determinant of matrices, all the heads are matrices, and we have also quadratic term here where inside we have a matrix. Fine, so now we can move on, and now that we have a conditional distribution, next question is how to get the marginal distribution and joint distribution. So identically, the same as what we did before, with the only difference now we have many q's and many x's. So q's are the weights and biases, x's are the non-trainable states of neurons. We follow exactly the same analysis. We put a constraint on the free energy. the Lagrange multiplier alpha that imposes this constraint plays the role of the inverse temperature. Everything is the same. Now the probability distribution has again those two terms. One is the determinant to this fixed power, and the other one is the exponent that has of the Gaussian distribution. So this is basically a Gaussian distribution, a multivariable Gaussian distribution. So this is the term that comes just from thermodynamics without learning. All right, this is the term that, for example, may come from the fact that you, in your loss function, you've included L2 regularization of weights. So the weights cannot become very large. You've constrained them. There is no runaway of the values of the weights, and so you have this exponent. And so if you run your code many times, you will see that having very large weights would be exponentially suppressed. Okay, so there's nothing interesting in that term. This is expected. Okay, however, then there is this again other term, which is determinant of to some power. So what does this term means? Now, of course, now it depends really what Q's are. And so Q's are the weights, and weights appear in this matrix. And so once I really take this determinant, it's not clear where the weights will go. Here we make this simple observation, just like we did before. Let's think about the trainable variables. Let's just think about expanding it to the second order. And now of this whole result of this determinant, right? And if we expand it to the second order, then something like this will appear. So you'll have a product of terms where each of them is quadratic. So maybe the way to think about this, we diagonalize it and think about each term in the diagonal being quadratic in Q. Now, this step going from here to here is not really a correct step, because you really need to know what the trainable variables are, how they appear in the determinant. You have to do this work, and once you're done, then you will have some power law expression here. And once you have that, then you have to raise it all to some power and see the overall probability distribution. Now, it may not factor just like it factors here, so it may have more difficult terms here, but here we don't do that. But actually, going from here to here, it's okay, because you can always choose diagonal representation. But later on, what we're going to do, we're going to assume that those individual Q's are actually weights. And we're going to say, all right, let's study the dynamics of weights, and maybe the dynamic of weights will have to form this power law distribution. In addition to this exponent. So if we have to see this exponent, if we don't see this exponent, then something incorrect happens, because we do know that infinitely very large values of weights have to be exponentially suppressed. Okay, so then we have this two regimes: smaller fluctuation described by scale invariance spectrum coming from this determinant, and larger fluctuations are coming from the Gaussian. Not very different from what we thought. The only complications now, we have many terms, and so there are many variables. Questions? Yeah, guess people want to see numerical results. Okay, so let's get there. We may come to the analytics later. So let's see a concrete numerical simulation that was done to confirm this power law correlations, power law distributions. Now, this simulation is actually, this numerical experiment is more complex than it should be, and later it was confirmed that the same result can be obtained for much simpler data sets, and also more complicated data sets, and for much simpler and for different activation functions. But for the concreteness, we took the MNIST data set. So it's a data set of the handwritten images, just like what we had for other experiments. We have 60,000 training samples and 10,000 test samples. Again, this number could have been smaller. The network could have been smaller as well, but we just took it to see that there's nothing changes when we make things bigger. Okay, now we have a fully connected feed-forward network with only 2 hidden layers. Again, nothing is expected to change if we take an unconstrained network or something like that. This is the number of neurons of the 2 hidden layers. The activation function was chosen to be ReLU. Again, other activation functions had been tried with essentially the same results. It was optimized using stochastic gradient descent, batch size 1. So that's important. So we're not really trying here to accomplish the best possible learning efficiency. What we are trying to do here by making this batch size small, we're trying to enhance the fluctuations to really see what they are. And so the batch size was chosen to be very small. Learning rate was taken like this. And so, as I say here, the choice was such that to enhance, so that we start seeing this power law distributions earlier on. Okay, so now we do use this L2 regularization term that I've mentioned in passing, because this is important for us to reach equilibrium. If we wouldn't have that term, then the weights can run away, and then there would be no equilibrium reached. And so that's equivalent to having a mass squared term in the loss function with mass squared given equals to 5 times 10 to the minus 4. So that's to prevent runaway solutions of the trainable variables and to reach equilibrium. We trained for 3,000 epochs, so it's a very long time. Now, effects that I'm going to show can be seen earlier, but here we trained it for a very long time. So there are many passes through the data set. And that ensures that we are in the learning equilibrium. So having too few passes wouldn't be enough, but now may not be enough, but now we are guaranteed that we are deep in the equilibrium. And now we keep track of the loss function for the test data as well. So to make sure that there is no overfitting, because overfitting is a separate effect. Now it's important for us to isolate the effect. We don't want to make sure that whatever we see is not due to overfitting, but a generic property of the learning system. Okay, so now I start with, so the next few slides, I'll just show you different probability distributions and we'll discuss them. Let's start with this one. So it's a conditional distribution. This is distribution of the non-trainable variables given some set of the trainable variables. How do we get that? We train it for some time, for many epochs, then we stop changing weights, and we go through one epoch. And through one epoch, the state of a given neuron takes different values, and we just plot the distribution. Now, since we used ReLU, there will not be any outputs to the negative x. So the whole distribution is only on the positive x. Now, potentially, the values of x are unbounded, so they can be anything. They can be as far away to the right as they want to be. What is important to note here is that the 2 peaks are formed. So, that's very important. Now, they would have been more symmetric if our activation function would have been hyperbolic tangent, but even here you can see those 2 peaks formed. This is the classification that the given neuron is making. So it's either fires or doesn't fire, depending or on its state. Okay, so we have 1 peak and we have 2 peaks, and that seems to be similar to all neurons. Only 4 neurons are plotted here, but in general, you can have many more. Well, you can look at all of them. They'll all start classifying, forming double peaks. The live neurons will start classifying. Okay, any questions about the plot of the conditional distribution? Okay, so let's move. Go ahead.
Is it possible to see the temperature values from here on the range?
Can you say it again?
Is it possible to see like temperature?
Oh, I see. Okay, is it possible to see a temperature from here? Okay, so from this particular distribution, so if we take a log, then it would be like, so log of the distribution would be minus beta times the loss function, right? So presumably you can try to extract what the beta is, but for that you need to yeah, so I don't know even from, I don't know how to do it from this plot alone. So usually to see the temperature, what you have to do, okay, well, I do know. So, okay, so you have distribution here. From this distribution, you can estimate its entropy. Okay, entropy of this distribution. This is S sub X. Now, what we are trying to see, the temperature is du ds sub X. So what we want to see how the U loss function changes with the change in the entropy. Now, as you train, the S changes, S sub X becomes smaller and smaller, and then U changes. And so you can try to see how, by how much U changes with respect to entropy of those distributions. So there'll be du dsx, and that will be temperature. Okay. Now, an interesting effect is that you may see this temperature negative at certain stages, and then the positive and the other stage. But it's du dsx which determine temperature. So from this plots alone, you cannot, but from the evolution of those plots, you would be able to.
Thank you. Are these double peaks we're seeing here related to the double descent we discussed some time ago? You know, there were these cases of under and over parameterization.
Oh, no. Those two peaks are classification. So the horizontally is the value of X. So those two peaks are actually showing you now. Okay, whether over parameterization is related to how the temperature of the trainable variables changes, I think it does, and so but it is not of the trainable variables. So here we are talking about the temperature of the non-trainable variables, and so those temperatures do not contain information about the over parameterization, as far as I understand. They are more about how well the system learned, right? So du ds, how beneficial. For example, you can calculate. So I already said du dsx would be the temperature of the non-trainable variables, but you can also and so basically, you know, how much easier would it be for you? You can also start adding the non-trainable variables and try to see how the U changes. So maybe if some neuron becomes dead and then you add it to the system, how the learning will benefit. So that's another thing. In one of the lectures, we describes the benefit of adding new neurons, and that's another thing that you can try to extract. But it's not about non-trainable variables yet. We are getting there. So let's keep going.
So, quick question. So this is without any training. This is just randomly initialized.
No. Oh, sorry, I will have to repeat it again. It's after training. So you train it for a long time, and then you freeze your weights.
Oh, okay.
So you would not see double peaks if it was without training. It would be just some kind of.
Yeah, that's why I was wondering. Like,
yeah, double peaks are a result of the classification that neurons are taking place, and that is only a result of the training. It's only after the training that you would see. So sorry, that's an important point. Okay.
And this is also tanh, right? Or ReLU?
No, that's ReLU. So that's why it's unbounded on the right. See, X can go.
Oh, right. Yeah.
So if it was hyperbolic tangent, it would be from -1 to 1, and then you would see 2 peaks, and they would be like more symmetric. I mean, they would still move left and right, but yeah. And with training, those peaks become narrower and narrower, meaning that entropy becomes smaller and smaller. Okay. So, and that's how you know that the temperature is positive. Why? Because with training, du becomes smaller and smaller. So average loss becomes smaller and smaller, and entropy becomes smaller and smaller, Sx. And so du dsx therefore is positive. And so that's how you know that at late times, entropy, temperature of the non-trainable variables is positive. Okay, so so this is only for non-training. Now let's move to the distribution of the trainable variable. Again, after training, here's what you see. Now, the only difference here from what we actually calculated here is I'm not going to be plotting the distribution of W's, but in changes in W's. Now, that's not the same. Now, it would, so the way you should think about this is that the mean Q bar, what was Q bar, may be changing. And then what we are trying to see is what is the distribution around the changing Q bar. So there's like semi-stable minima, and then the fluctuations we think are describing actual distribution for W's around that minimum. Now, of course, that's not the same. So really, what we really want to see is both distribution of the W's and distribution of DW's. There are two variables, what the W is, or what trainable variables, and how it changes. And then we are really, what we want to model is the distribution over paths. And in one of the first lectures, I think in the second one, when discussing the non-trainable variables, I mentioned that if you want to write down a probability distribution for paths other than individual states, then you have to write some kind of functional, right, distribution over paths. So here we're kind of putting under the rug and say, okay, the proxy for the distribution of the trainable variables will be the distribution of the jumps in the trainable variables, and the jumps that would describe which something that we will be plotting. Okay, so this is a distribution in changes of the trainable variables in 2 timestamp from t to t plus 1. And as you see, they are forming 2 different regimes. So there's this regime where this line is straight, and there's a regime where it starts to curve down, straight and curves down, straight and curves down. This is logarithmic versus logarithmic scale. Now, since it's logarithmic versus logarithmic, everything that looks straight is a power law. And everything that curves down here is not a power law, but we don't know what this path is unless we change the axis. So now, if we wanted to see that this guy is actually a Gaussian, then what we need to plot here on the horizontal axis, we have to plot square root of the log versus this. And then there will be a straight line. Or alternatively, we can plot log here versus quadratic here. And then it would be, should have been a straight line. But here the plot is log versus log. And so everything straight indicates that this particular, so it tells you that the jumps in the weights form a power law spectrum. Okay. Now, what it means also that those large jumps are not suppressed, right? So very large jumps are suppressed. There is a Gaussianity, but there is a large range of scales where things are not suppressed. Okay, so now, so in terms of formulas, we also see this. This is for large scales, you have power law. For very large scales, you have Gaussian, so that agrees with what we've discovered analytically. Now, the same plot, but to emphasize to show you that the second regime is actually a Gaussian, what we are plotting here now, log versus quadratic. So that's what I suggested we should do. And then in the log versus quadratic for very large jumps, you see that there are straight lines. So this is a Gaussian distribution. There are Gaussian tails. Now, but all the other ones, their smaller scales are not Gaussian. See, they come up, and they come up because of that, because they are power law, just like here. Okay, so are there any questions about this two plots, either the previous one or this? I don't know why this is highlighted, but something funny here.
Yeah, I'm a little confused. So, like, why are you focusing on the changes in the trainable parameter, the weights? Because
Yeah.
usually in my experience, the order parameter is like the activity of the neuron. And that's usually what people measure to see the log.
Yeah, so activity is
scale.
this. Yeah, activity is this of neurons.
Yeah, which doesn't really look scale free.
There's no scale invariance here, and it just develops two peaks. So there's nothing scale invariant there. There's no criticality here. Right. So now the only criticality, and we were not expecting to see criticality here from the derivations that we did before, right? Because basically what happens with those variables, they're fast changing variables. They quickly go to some state, but then they determine the state of the trainable variables. So here you don't see anything, and you have to concentrate on the trainable variables. Now I can also kind of explain why the trainable variables have this criticality. So and why it's good to have criticality. So think about this: that you have trainable variables are trying to find features in your data set, and let's say they didn't have criticality, then they would just be looking at the features at a certain scale, and that's it. Okay, and then the features of that scale they would identify, everything else they wouldn't identify. Now, however, if they trying to jump on all possible scales, right, then they are able to see features on all possible scales, and that's what we want. So if we have a picture of handwritten image, then presumably there are different scales on which features are important, or anything else, any picture, right? And then having this ability to actually learn and jump on different scales enables you to learn first. So I don't think there is any criticality here, okay? But there is a criticality here. Now, however, if we would be looking at the changes of the states of neurons, that can also have features of criticality, but that was not explored. So we're not expecting to see it in the P of X, and so we didn't see it either. But we do expect it to see in the P of Q, and we do see there. And we actually know where it comes from. It comes from this logarithm. Actually, like coming back, maybe now it's time to come back and to see where does it come from. It comes from this. It comes from the coupling from the loss function, right? So, for example, when you use mean squared error, it is what you're throwing mean squared error at the output layer. What you put there as an expression has 2 powers of x and has 2 powers of weights or q's, and because of that coupling that happens in the definition of your loss function, you get this logarithm in the free energy, and because of this logarithm you get this power law that tells you that at small scales you should see that's straight behavior. And that's other questions. Now, in more biological context, people, when they're looking at the power law, they do see criticality, like in the activities of neurons, but those are like temporal criticalities. So again, maybe that's what Vladimir was talking about. When you look at how the state of the neuron changes with time, then you look at this time series and they see that the power spectrum, that there are fluctuations on all temporal scales. So this is a fluctuation of the spatial scales, if you want, the scales of the values of the weights rather than on how time sequence progresses. Okay, let's move on. So the other thing we wanted to confirm, now usually this is not how self-organized criticality is analyzed. It's usually analyzed by looking at the power spectrum, and so we decided to look at the power spectrum here. Now, so we are looking at the temporal change. So now W is a function of t, right? And we're trying to analyze what is this function is. Let's look at that function. Let's take it power spectrum and then see what that power spectrum is. Now, if the individual jumps in W are completely uncorrelated, so you have W and then it makes in the equilibrium. So each weight makes uncorrelated jumps. Every next jump doesn't depend on the previous one. Now, what the distribution of jumps, it can be arbitrary, doesn't matter. But what's important that every next jump is dependent on the previous one. If that's the case, then you can just calculate the power spectrum. Okay. Now, and then you will see that the power spectrum will be given by 1 over f squared. So that will be the scaling. So P of f will be, you can just derive it. This is not, for example, a random walk. So if you take a random walk where the jumps are drawn from some distribution, then the power spectrum of this time series will be given by 1 over f squared. Okay, but we want to see deviations. What we are saying that individual jumps in the weights are not uncorrelated. And so the previous jumps determine the next jumps you're going to make. And for that, you need to plot f squared P of f. And so if they are uncorrelated jumps, then it will be a straight line. If they're correlated, that will be something that is different from a straight line. So what we see that the low frequency fluctuations, meaning very large fluctuations, are independent. Okay, so if you make a very large jump, you hit the wall in the space of the trainable variables, and you should come back. And so that wall is like parabola. So if you're looking at your system in a very coarse-grained way, then there is really this parabola, and the large jumps. If you jump one way, then they are kind of uncorrelated and form some distribution. Now, however, this tiny jumps, small jumps, they are not uncorrelated, and there is some feature to this. Okay. Okay. So let's see. So yeah, and then you can see that there is this for low frequency. Oh, sorry, it's other way around. So for the low frequency jumps, actually it forms parallel law, and the high frequency do not form parallel. So it's other way around. I should rephrase it. So the tiny jumps are uncorrelated, but the long jumps becomes more and more correlated according to this. Okay, so let's move on. Okay, so now let's see how this changes. Actually, let's take one weight and see what does it do at early times and at late times. So this is after one epoch. This is how the system looks like. So there is no criticality here. You have the integral, and then there are positive and negative jumps. So which way the weight will go, of course, the term is arbitrary. It can go to the left or to the right. It can increase or decrease its value. But the very large jumps are exponentially suppressed. This is after one epoch. Now there's a symmetry. So you go one way more than you go the other way, or just because the weight is slowly drifting to the value where it wants to be. So that's the drift. Now, but in the long run, when you come to the equilibrium, the average value of the weight becomes more or less zero. And then you see this very straight distribution. Now, the only difference from the previous times is now I have making a sample average. So I basically averaging over weights, over all weights, and then you see this distribution here. Okay, again, you had no power law distribution in the beginning, and then in the long run you had W power law distribution, because on the log scale looks straight. Okay, are there any questions about that? Now this is here like the fluctuations of all weights taken into account. So all combined together, not individual weights, but all the weights combined together.
Have you looked at like the progression of this distribution as a function of the epochs? Because I remember you were saying that the training kind of goes from phase transition to phase transition, which my guess would be then like this log scale or scale-free distribution power law would like set in, say, at epoch 100, and then it would kind of just stay fixed, or like it would
I understand. So maybe there'll be
as it's training.
Yeah, so there'll be sharp.
That's like a
Maybe
verification
there
of
will be
that.
sharp jumps from here to here, right? That's.
Well, no. So as it's training, like it will stay as a power law, maybe like changing the exponent,
Yeah.
but it will remain a power law while your accuracy is improving. Like,
Right.
would that be like a verification of what you were saying earlier?
Yeah. So I think you're right. So basically, I think what Vladimir is saying is that as the learning progresses, first you start with the Gaussian distribution of the trainable variables, and then as training progresses, this Gaussian distribution of the non-trainable variables, they start to form double peaks, right? So they for one Gaussian splits in two Gaussian, two in the four, and so forth and so forth. And that splitting is like phase transition, and those phase transition are what give rise to the criticality. So my expectation would be that because of each of this phase transition, this the power law distribution that you see here just becomes longer and longer. There are more and more scales on which now the power law jumps are allowed. First, they were all confined to a signal Gaussian, and so all of them were exponentially suppressed, and that's what you see on the left. And there will be now more and more flat directions established. And as you establish this flat directions, their respective trainable variables starts making like more frustrated jumps in this direction. Now, another important point to make is that we also only expect to see the scale invariant jumps in the systems where flat directions are established, right? In the space of the trainable variables, because if there are no flat directions, if the mass is positive squared, or then there is only Gaussian distribution can be formed. So this is an indication. Once you see the scale invariance, this indication also that there's some kind of symmetries or flat directions are formed. Emergent symmetries are formed through the evolution. Now, the one thing is not clear, remains unclear whether those flat directions of the symmetry are formed because the training data set had some symmetries, or it is just a generic feature of learning. So, for example, we know that there is a symmetry, underlying symmetry in the convolutional neural networks. Right now, why? Because the data set had certain symmetry, and so that translates in a trained data set. But do you get the symmetries because the training data set had it, or you establish those symmetries automatically? Now, for example, would you have the same criticality if there would be any criticality in the training data set? There would be no, and that's not clear. So that's not clear whether how the symmetries from the boundary dynamics are translated into the symmetries or scale invariance, and then boundary dynamics translates it into the scale invariance of the training network.
Okay, so I see. So you're saying that it would keep extending, like becoming longer on the X scale.
Yeah,
this
that's
power law.
the guess. That's
Okay.
the guess. Right.
Yeah.
And so there will be like the range of the scales on which it's has scale invariance, which just grow longer and longer.
Okay.
With more and more phase transition. Mm-hmm. Yes. Other questions?
Are you aware like of scale invariance in the MNIST data set that you used here?
Yeah, so we kind of we don't see it, right? Okay, so that's a question. So there is some kind of question of the two things. MNIST dataset has locality, meaning that the dark pixel is more likely to be dark if the close by pixel is dark, right? So there is a notion of locality. There is a notion of symmetry there, presumably. So there is like reflection symmetry. There are probably shift symmetries. So that we have in this data set, just because it's an image. Any image would have that. Now those things, and in addition to that, you have long distance correlations. If you have I don't know, some digit written, that means that if you see a dark pixel on one side, now it's low likely that in that direction you will see another pixel because you draw lines, right, when you write images. So the long distance correlations and symmetries are present in the NIST data set. Now, and those are this is what we know about, right? Now, criticality seems to be telling us that it also establishes some kind of long distance correlation. That's what criticality is. Scale invariance, right? So you don't have your correlators are not exponentially suppressed, but they extend in the larger direction. Now, what we can potentially do just to test that this is not unique to the data set, but to choose random images. It doesn't matter that they don't represent much, but some random images, then noise, like Ising model, if you're familiar with Ising model at high temperatures, so there are no long distance correlation. Then see whether they establish criticality. Now, if they something like this, so if they do establish criticality, then it proves that the criticality doesn't come from the training data set; it's intrinsic to learning, and that's my guess. Now, if they don't establish criticality, then it's telling you that that something about the data set that translated into criticality here. So both results would be interesting, but for now, I don't know that.
Yeah, that would be an interesting test to
Yeah.
run. Although I'm not 100% sure what the class would be, like the two classes would be for high temperature Ising model.
Well, I mean,
Because-
you don't have two classes, right? So for the Ising model, what you can do outing quarter. There are other things you can do, right? So I mean, it's
Right,
not
okay, yeah.
important. But I think the point is, it's not important what the boundary dynamics is, but it's important what the correlators and the boundary dynamics are.
Right.
And that, like, how those correlators are being translated into correlators in the bulk. So yeah, so even having like no output or like in the outing encoder output equals to input, it's enough to ask that question. Interesting question.
Got it. Thanks.
Sure. Okay, so now more about symmetries next time, because that's kind of an important question. Now, identifying symmetries within your boundary dynamics and then developing your neural network such that it has those symmetries is important. And then you can say, well, it can either a network will guess it itself or will help it. Will help to say what the symmetries are, will help to say what the irrelevant and irrelevant information. So next time we'll discuss one such example. And that has to do with the latest paper that we wrote about with Nicola about autonomous particles. And then it will also be extended and to the in the last lecture or to the biological setups. But that's kind of the idea. Let's see if there are any other questions on the scale invariance, and then if not, we'll stop here. All right, thank you guys. I'll see all of you next time then.